half-life period of a reaction, which is time during which the concentration of the reactants is reduced to half of its initial. That point indicates the half-life of a reaction. That half-life of zeroth order reaction is directly proportional to initial concentration. Has a half-life period 7. The concentration is reduced to experimental determination of order of reaction. So there are 5 methods which we use versus concentration of the reactant. Next, square of the concentration of the reactant are different. Then we need to move for the next integrated rate equation, that is integrated rate equation for the concentration of the reactant that time constant. The concentration of A versus time graph is plotted. Let's mark a point. The total order of reaction is. Hello students, welcome to Learn It. Now we are going to discuss about important concept, that is half-life period of a reaction, which is indicated by T half. It is the time during which the concentration of the reactants is reduced to half of its initial concentration, or it is the time in which half of the reaction is completed. Let us take one example, that is conversion of ice into water at constant temperature. So it takes around 2 minutes to become ice to water. So 2 minutes is called as lifetime of a reaction, whereas half of that lifetime of reaction is called as half-life period of reaction. If you take 2 grams of ice, that is called as initial concentration, but here we are taking in terms of mass. So if we take 2 grams of ice, so as to become it 1 gram, so the time taken is called as half-life period. So here it is 1 minute or 60 seconds. Another simple example we can take so as to visualize this half-life period is decomposition of hydrogen peroxide. Simultaneously we are plotting a graph of concentration of hydrogen peroxide versus time. So let's 1 mole be the initial concentration of the reactant, which is indicated in the y-axis. When the reaction is carried out, there will be formation of water and oxygen, simultaneously decreasing the concentration of hydrogen peroxide. So here the students must consider that we have not taken the concentration of hydrogen peroxide to exactly 0, because we know there will be equilibrium concentration. So hydrogen peroxide cannot be 100% converting to water and oxygen at certain temperature. Based on this graph, we can calculate the half of the initial concentration by 0.5 mole, which is exactly at the midpoint of the initial concentration. And if we draw a straight line along x-axis or parallel to x-axis, and we need to note down the point on the curve, and if we draw a straight line which is along the y-axis, and which if it cuts the x-axis, then that point indicates the half-life of a reaction. So remember, this is a graph of concentration of the reactant versus time. Now we are going to discuss a half-life period with different order of reactions. So first one is half-life period of zeroth order reaction. So as we know, with respect to half-life period, the concentration of the reactant is reduced to its half. When we put this into integrated rate equation for zeroth order reaction, that is K is equal to concentration of R0 minus concentration of R divided by T, we get T half is equal to concentration of R0 minus concentration of R0 divided by 2 divided by K. Then T half is equal to concentration of R0 divided by 2K. So by this we understood that half-life of zeroth order reaction is directly proportional to initial concentration. It means if we change the initial concentration of the reactant, then its half-life will also change. So for general example, we can say like a person eats a pizza at a constant speed, no matter the size of the pizza given to him. So it means the speed of eating that pizza is independent on the size of that pizza. Consider a situation where a person is given small size pizza. So as to finish it, let us assume that he takes 5 minutes. So the half-life will be 2.5 minutes. Let's consider another situation where a person is given double the size of previous pizza. Hence it is concluded that so as to finish it, he takes double the time which is previously taken. So half-life period will also doubles. If we plot a graph of half-life period with respect to initial concentration for zeroth order reaction, we'll get a straight line which is passing through origin with a slope of 1 by 2k. This graph indicates as the initial concentration of the reactants increases, the half-life period also increases. Now let's discuss about the half-life period of first order reaction. Here we have integrated rate equation for first order reaction, which is K1 is equal to 2.303 divided by T log of concentration of R0 divided by concentration of R. So as we know, at T half, that is at half-life, the concentration of the reactant is reduced to half of its initial concentration. That's why concentration of R is converted into concentration of R0 divided by 2. So T half is equal to 2.303 divided by K1 log of concentration of R0 divided by concentration of R0 divided by 2. So if we take the 2 above, then it is going to become T half is equal to 2.303 divided by K1 log of 2, because R0 and R0 got cancelled. So the value of log 2 is 0.301. So that's why 0.301 into 2.303, it is going to give us 0.691. So T half is equal to 0.691 divided by K1. If we plot a graph of T half versus initial concentration of the reactant, it is going to give us the straight line which is parallel to x-axis. It means the half-life period of first order reaction is independent on the initial concentration of the reactant. We have seen this example in nuclear chemistry. There we have come across one concept, that is half-life period of radioactive substance. For example, uranium-235 has a half-life period of 703, that is 703 million years. No matter the initial concentration of the substance taken, the uranium-235 is always having the half-life period of 703 million years. If we take 1 gram of uranium-235, so as it to become 0.5 gram, it takes 703 million years. Like that, if we take 10 grams of uranium-235, so as to become 5 grams, it takes 703 million years. In conclusion, we can say it takes 2 half-life period for first order reaction to become 25% of initial concentration. It takes 3 half-life period so as to become 12.5% of the initial concentration, and so on. Remember, first order reaction is not going to complete 100%, meaning the reaction can approach completion but won't be 100% complete in a finite time. If we consider the initial concentration of the reactant R0, then after first half-life period, the concentration is reduced to R0 divided by 2. After second half-life period, the concentration is reduced to its half, that is R0 divided by 4. After third half-life period, the concentration is reduced to half of the before concentration, that is R0 divided by 4 divided by 2, that is equal to R0 by 8. So if we continue this, then after nth half-life period, the concentration is reduced to R naught divided by 2 raised to n. Now let's look at the half-life of second order reaction. So with respect to second order reaction, we have the integrated rate equation. So at half-life, the concentration of the reactant is reduced to half of initial concentration. So which when we put in integrated rate equation, we get K into T half is equal to 1 by concentration of R naught divided by 2 minus 1 by concentration of R naught. So when 2 goes up, then it will be K into T half is equal to 2 by concentration of R naught minus 1 by concentration of R naught. So this will become K into T half is equal to 1 by concentration of R naught. So when K is replaced its position, then T half is equal to 1 by concentration of R naught into K. So that's why by this we can conclude that half-life is inversely proportional to initial concentration of the reactant in case of second order reaction. So in conclusion, we can say for zeroth order reaction, half-life is directly proportional to initial concentration. For first order reaction, half-life is independent on the initial concentration of reactant. So for second order reaction, the half-life period is inversely proportional to initial concentration of the reactant. So for nth order reaction, half-life period is directly proportional to initial concentration of the reactant whose power is 1 minus n. That is, half-life period of nth order reaction is inversely proportional to n minus 1th power of initial concentration of the reactant. Next important concept with respect to chemical kinetics is experimental determination of order of reaction. So there are 5 methods which we use practically so as to determine the order of reaction. The first one is graphical method, second one is use of integrated rate equation, third one is initial rate method, fourth one is Ostwald's isolation method, and the last one is half-life period method. We'll discuss one by one. So the first one is graphical method. So this method is suitable for the reaction which is involving only one reactant. And the steps involved are, first one, we are going to calculate the concentration of the reactants at different time interval by using suitable method. Second one is a graph is plotted, that is the concentration versus time. And the instantaneous rate is determined at specific intervals by drawing a tangent and finding its slope. So next, the rate of the reaction is plotted versus concentration of the reactant. Next, square of the concentration of the reactant and cube of the concentration of the reactant, and so on. If we get a straight line which is parallel to x-axis in rate versus concentration of the reactant graph, then it is understood that rate is independent on the concentration of the reactant, then it is zeroth order reaction. If rate of the reaction versus concentration of the reactant graph gives a straight line which is passing through the origin, then the reaction is first order. If we get a straight line which is passing through the origin in rate versus square of the concentration graph, then this indicates the second order reaction. Similarly, if we plot a graph of rate of reaction versus cube of the concentration of the reactant, then if we get a straight line which is passing through the origin with a certain slope, then that reaction is of third order, and so on. So let's discuss one example that we are going to calculate order of reaction by using the graphical method. The example is decomposition of nitrogen pentoxide or dinitrogen pentoxide, and we have the rate data with respect to concentration of the reactant. When we plot a graph of rate versus concentration of the reactant, that is concentration of dinitrogen pentoxide, we get a straight line with a certain slope which is passing through the origin. This indicates the reaction is of first order. But when we plot a graph of rate versus square of the concentration, we get a curve. This indicates this reaction is not second order. Then rate law can be deduced as rate is equal to K into concentration of nitrogen pentoxide. The value of K, that is rate constant, is calculated by two methods. The first one is by measuring the slope of this straight line, we can get the value of K. The second one is we can take one example. So in that we have a reading for concentration of nitrogen pentoxide and corresponding rate. So if we divide the rate by concentration of the nitrogen pentoxide, we get the value of K. Next method for the determination of order of reaction is use of integrated rate equation. So this method is also called as trial and error method. In this method, the kinetic data is fitted into the equation for the correct order of reaction. So the equation will give constant value of rate constant for all the data points, that is concentration at different times. So consider one example. We have the kinetic data for certain reaction. We are having the initial concentration of the reactant, and after certain time it changes to certain concentration, that is indicated like concentration of R. So this initial concentration, that is R0, concentration R at time t, put into the integrated rate equation for zeroth order reaction. So we get certain value of K. So we take the another one trial, that is a concentration after certain time t, that is before it was T1, now consider after certain time T2, the concentration is reduced to another concentration, that is R. So if we put these value in the integrated rate equation, if the K remains same for integrated rate equation of zeroth order reaction, then it is considered that the zeroth order reaction. If these two values are different, then we need to move for the next integrated rate equation, that is integrated rate equation for first order reaction. That time, if both the values of K are same, then it is considered that the reaction is of first order. If not, we need to move on to next integrated rate equation, that is integrated rate equation for second order reaction. In conclusion, we can say that we use the kinetic data and put it into different integrated rate equations. And whatever the integrated rate equation gives the constant value of K is the order of reaction. So next important method of determination of order of reaction is initial rate method. So this method is suitable for the reactions which are having more than one reactants. Consider a hypothetical reaction in which there are two reactants A and B which are reacting to give products. So consider we are going to keep the concentration of the reactant B constant, and we are determining the change in the initial rate with respect to the concentration of reactant A. Keeping the concentration of the reactant B constant, the concentration of A versus time graph is plotted. Let's mark a point at the initial concentration and draw a tangent with respect to that curve at that point. The slope of that tangent is going to give us a rate which is called as initial rate 1. Let's double the concentration of A, and the concentration of A versus time graph is plotted. The initial point is noted and the tangent is drawn, the slope is going to give us the initial rate 2 at double the concentration of A. Now initial rate 2 and initial rate 1 are compared. If initial rate 2 is equal to initial rate 1, then there is no difference in the rate of the reaction after doubling the concentration. So the rate of reaction is independent on the initial concentration of the reactant. So the reaction will be of zeroth order. So if initial rate 2 is equal to 2 into initial rate 1, or initial rate is twice the initial rate of 1, then it is understood that after doubling the concentration, the rate also doubled. So it means the order with respect to concentration of A is 1. So if initial rate 2 is 4 times the initial rate of 1, it means that after doubling the concentration of A, the rate increased to 4 times. So it means the order with respect to concentration of A is 2, or the second order reaction. The order with respect to B is calculated by keeping the concentration of the reactant A constant and repeating the procedure. So the order with respect to A and order with respect to B are added so as to get the order of a overall reaction. Let's look at one example. Here 3 experiments are conducted with respect to concentration of A and concentration of B, and corresponding rate of reaction is determined. In experiment number 1 and 2, the concentration of B is kept constant, but the concentration of A is doubled. The rate of reaction is increased by 4 times. So it resembles the second order reaction. With respect to experiment 2 and experiment 3, the concentration of A is kept constant, but the concentration of B is increased by 3 times. 0.01 into 3 times is equal to 0.03. So the rate of reaction is increased by 3 times. So that's why the order with respect to concentration of B is 1. So the total order of reaction is 2 plus 1 is equal to 3. Next method for the determination of order of reaction is Ostwald's isolation method. This method helps to determine the order of reaction by simplifying the kinetics. For instance, in a reaction involving A and B, you can keep A's concentration very high. This means any change in the reaction rate mainly depends on B. By varying B's concentration and observing the rate, you can determine the order with respect to B. Similarly, the process is repeated by taking the concentration of B in excess. Order with respect to A is calculated. The overall order is calculated by adding the order with respect to A and order with respect to B. The last method of determination of order of reaction is half-life period method. So here we have a relationship between half-life period and initial concentration of the reactant. It is T half is inversely proportional to initial concentration of the reactants whose power is n minus 1, where n is order of reaction. So let's consider a case if C1 is the initial concentration of the reactant and half-life period is T half of 1. If initial concentration of the reactant is C2 and half-life period is T half of 2, then by the above relation we can get like T half of 1 divided by T half of 2 is equal to C2 divided by C1 whose power is n minus 1. So when we rearrange by taking the log on both sides, we get n is equal to 1 plus log of T half of 1 divided by T half of 2 divided by log of C2 divided by C1.